Hello, everyone, and welcome to episode number 37 of the Hyperthesis Podcast. I'm Patrick.
I'm Pheely.
I'm Liam.
I'm Zoe.
So, as you can tell from our intro, we have a very special guest on today. We have Zoë Vestrum, who will be joining us to talk about her interests and her research in geophysics. We'll introduce more on that soon, but she does study geophysics at the University of Alberta. I've known her for quite a number of years. She was one of my first friends at the U of A, and her work is very cool and hot, I would say. Yeah.
Literally.
Spicy.
Yes, very spicy. But before then, we'll just do some quick intro topics. Does anyone have any intro topics they would like to discuss?
I have a correction from a previous episode before we do an intro topic. In episode 35, what did I say? I said that metamaterials are these things with negative refractive indexes, but that's just a specific case of metamaterial. I think the metamaterials are just defined as materials that do things that normal materials in nature don't. So it's a pretty kind of broad definition. And one of our previous guests, Dean, pointed that out to me. So that was episode 35 where I made that mistake. Anyway, just figured I'd point it out. All right, intro topics. Let's go.
So I have a quick intro topic. It's a little bit depressing, but has to do with climate change. The IPCC, or the Intergovernmental Panel for Climate Change, just released a synthesis report of essentially all their different reports, and it takes together a lot of different scientific work over the past few years that looks at climate change. And essentially what this report said was, we're screwed in the short. In the long, it says that to be under the 1.5 degrees Celsius limit that was set for the Paris Climate Accords in 2015, we would essentially have to stop all CO2 production or greenhouse gas production by 2030 and actually have to start absorbing more in order to not go over that threshold, which at this point is not going to happen given the current state of the world. So we are not on track to stay under 1.5 degrees Celsius of warming compared to pre-industrial levels. We also aren't on track for the worst case scenario, which is like 8 or 9 degrees of warming, or it might be, between 5 and 8 degrees. So that's good, but we're probably going to settle around 2 to 3 degrees of warming, which will be still pretty disastrous. So if you want to go check out the actual report, it's extremely long, but they also have shorter summaries on their website for both the media and for, I guess, government officials who aren't scientists and don't want to read through a scientific report. But kind of doom and gloom, but that's the world we live in.
I wonder if they did, or probably they did, a calculation of how much glacier would melt from that rise in temperature, and it's probably related to how much sea level would rise, and salinity is also an issue too, right? If it's too much, but I don't know too much about it.
I know. I think somewhere in the report they said that the sea levels have gone up by about 1 centimeter on average, which doesn't sound bad, but considering the surface area of the ocean, that's quite a bit. Just for reference, if Antarctica and Greenland were to melt, it goes up by 60 to 70 meters.
Right, and also the Dutch people is gonna be in trouble.
How does that work? Like I've always hear that the Netherlands is below sea level. A lot of it is. How's that work?
They build a wall.
Okay. I've heard that before, but like, how big is this wall? Where is it? What's it do?
I mean, it's, I think they call it a dike there. And essentially it's this very long seawall. I think for Liam, the Pictou Causeway, but
The Pictou
better.
Causeway. Only like 4 people on the Earth will know what that means.
Yes.
Incredible.
But think that, but essentially along a majority of the coastline of the country.
Okay.
And that's your protection system.
That would make me uneasy. I don't know about you, but not a lot of
Yes.
protection.
It's like a future Atlantis, right? Like humans years from now, once our generation is wiped off the earth for some reason, it just could be many, and they would look back and they're like, "There's one civilization underwater, and they're like, this is Atlantis, but it's just the Netherlands."
Well, and it started because they were sinking, and so then they had to like build this wall, but now they've actually moved it way out. So the Netherlands is bigger than it used to be because they're taking the sea.
Oh, they're conquering the sea. That's incredible.
Mm-hmm. It's like that. What's it in UAE? Was it UAE? It has like the Palm Island thing that they just put down some land. They just made land because there's so much money. They can just do that.
Yeah, we're doing like micro terraforming nowadays.
Imagine if like Singapore was like the artificial land, because it's in a way it's not that big, right? Like it's kind of tiny. Imagine like, no, you know what? I'm gonna go build a new island and just create a country there.
I mean, isn't that what Hong Kong is doing with parts of their area? They've actually grown in land mass. And I know they're planning a new airport that is proposed to sit on top of water. So they're reclaiming a whole bunch of land in Hong Kong, I believe.
It's strange to say reclaiming land. They're actually like just building land.
Just moving land from one place and putting it somewhere else.
True.
It's like Minecraft. It's like, I'm just gonna stack some blocks to make a land on water.
Anyway, before we get too much into it, are there any other intro topics people want to bring up?
I read an article talking about. It was a short article, so I don't have much to say on it. But some scientists somewhere in the world, they used muons to kind of image the inside of one of the Great Pyramids. I think it was Great Pyramid of Giza. So they fired muons into it and somehow measured them coming out the other side, and they could like map all the tunnels and stuff in the pyramid. And they found these extra voids, they called them, just these kind of empty holes in the pyramid that they didn't know about before. So that's kind of neat. I don't know how good muons are going through things, but I guess that's one way to measure. At least you could. I wonder how far into the Earth you could measure with muons. Probably not very far, right?
I mean, this is something that someone who was in the same lab that I did my master's in was researching, was muon propagation through the Earth, especially where SNOLAB is, or the Sudbury Neutrino Observatory, because they want to know how many muons are coming in, since that counts as background for any super sensitive detectors like dark matter detectors. And so the answer is not a lot. About 2 kilometers down, where the Sudbury Neutrino Observatory is, so probing to like the center of the Earth is much more difficult, and you probably wouldn't get a very strong signal.
Oh, I think talking about Snow Lab, right? I think they were approached by the military at some point about like having neutrinos as like secret signal to transmit code across the globe, because it go through everything, right? So if you have a detector across the globe, you can just send it directly to the Earth. You just go through it, and you have sensitive enough detector, you get it. But in terms of financially, it's not really feasible, or like it's really difficult to do.
Yeah, that's exactly what I thought of when I read this article about like using particle physics to image the inside of the Earth. I was like, you'd probably only be able to do it with neutrinos, as far as I'm aware, and you'd need really expensive and complicated detectors to do it, let alone to like determine anything, like to come to any conclusions. There's an episode of Star Trek that does that, actually, funnily enough. I remember watching it, and I think Geordie LaForge is like stranded on a planet with really, really bad electromagnetic storms, so he can't get a signal up to the Enterprise. But he's like, "Oh, I'll just create a neutrino beam with," and he whips together a neutrino beam with some pieces of metal or something. It's like, oh my god, kind of funny, but it was kind of neat actually, because I'm like, wow, if you want it to get through a really intense electromagnetic storm, like you want to send a signal through, and I'm like, I guess neutrinos would be the way to do it. So I thought that was kind of neat.
Well, I guess speaking about probing down into the Earth and finding out what's under there, we'll transition into our main topic, which is featuring our special guest, Zoë. So Zoë is a current PhD candidate at the University of Alberta, studying geophysics with Martin Unsworth. So she works on different systems, which we'll get into. She'll be able to explain them a lot better than I can. But I do know the name magentotellurics, which she's used. But there are probably other methods that you'll be discussing. Before then, she studied at the University of Saskatchewan with an Master of Science in Geophysics, looking at plate margin melt and how it's transported. And then she's originally from Calgary, so hasn't moved too far north, but to the better city in Alberta, I would say. And there she received her Bachelor of Science in Geophysics. So Zoë is definitely a geophysics person through and through. So welcome, Zoë.
Yeah, thanks for having me.
So what do you do?
So my specialization is in looking for geothermal energy using electromagnetics. So there's a bunch of different electromagnetic methods that you can use to basically scan the ground. It's a bit cheaper and easier than trying to figure out how to use neutrinos. So basically what happens is you have these, so magnetotellurics, which is my main method, we're using naturally occurring electromagnetic radiation, like literally from the sun. So the sun is making the northern lights, but the northern lights are also making these big kind of fluctuations in our magnetic field, which induce currents in the ground. And those currents are basically dependent on how well the ground conducts electricity, right? And so then what we're trying to figure out is, once you have that resistivity information about the ground, you could tell a few different things, like maybe rock types, or if there's water in it, or if the water's hot, that kind of thing. So yeah, that's what I'm up to in a nutshell.
Yeah, it's kind of small. Is it that much difference between each? Because I feel like there must be a lot of variance in resistivity just in like one material alone. Like because these are not pure rocks, for example. They are a conglomerate of things, or like they're mixtures, right? They are not made of one type of crystalline structure.
Yeah, so we're making big, like basically bulk measurements of these rocks, and we're making like pretty like low resolution images as well. So we're looking to, in my study, about 5 kilometers, and then the resolution is like 100 meters. So in that 100 meters, there's lots of different types of rocks. So at the near surface, we have some clays that'll have like sand, and it's really, heterogeneous. But when you're actually measuring it, you only get one measurement. It's like the resistivity's, like 10 ohmmeters. But then you have a granite underneath or something like that, and the resistivity is like 10,000 ohmmeters. And so then that contrast is what you're kind of looking for. And then if you have a fault that's running through it and it's carrying hot water, hot salty water is a lot more conductive than a cold crystalline granite. And so that's essentially what we're looking for.
So do you just put 2 probes in and send out a current and measure the voltage?
Oh, so it's actually kind of cool. So we have to measure the magnetic and the electric field at the surface. And so it's just a surface measurement. So we take electrodes and we put them in the ground 100 meters apart, north-south, 600 meters apart east-west, and then you're measuring the potential difference across them. That'll give you your electric field. And then you need to know your basically source magnetic field. And so then we have magnetic, like just basically solenoids that we also put out going north, south, east, west. And then the ratio between like the perpendicular fields will tell you about the resistivity of what's underneath, essentially.
This is the scale that I don't think we ever worked with before, because you remember in like physics lab, you put two probes together, like put on like circuits or breadboard and stuff. It's tiny, right? And you say electrodes are 100 meters apart. It's like, well, how can you even measure the voltage difference? Or does that really mean anything? Because like you're fucking two rods of metal really far apart but in a way, in terms of Earth scale, it's not far apart at all. It's like a dot, right? But in terms of human scale, it's really far apart.
Yeah, and what we're like trying to like the reason they're so far apart is that like you're measuring these really small currents in the ground, and so if you were trying to measure them close together, the amplitude would just be so small that you wouldn't be able to like measure it. And so the reason they're 100 meters apart is because then you have a lot more current to pick up, essentially.
So the current is gonna be it's gonna be really tiny current.
It's really
right?
tiny.
Like microamps or like smaller?
Yeah, I think they're milliamps.
Milliamps. That's
not too bad.
actually quite a lot.
Yeah.
Yeah. I'm surprised because milliamps, I think, is enough to kill people, technically.
Yeah, I think it's more about like the voltage than the amperage, I think, in the ground. That's mainly what we're looking at anyway.
I never heard about these method, but it sounds like, when you look at, for example, material like in the ground, you don't expect them to have high conductivity.
Well, no, and they don't, which is why we always talk about resistivity, is because when you're talking about conductivity, it's like, oh yeah, it's like 10 to the minus 5, like, Siemens per meter. And so, but it's like 1,000 ohm meters.
That's
or 10,000.
that's actually really low.
Yeah.
Only 1,000 ohms. Because you can have those resistors that are like 1 mega ohm or 1 million ohms easily, right? I was expecting like rocks to have a lot of resistivity for some reason, which I never looked up the numbers.
One point in your life, you just assumed that they would have very
just like extremely resistive
for some reason.
Yeah, they're not too bad. I think because they have like a lot of kind of fluid content, and then a lot of the fluids that are in them have a lot of like total dissolved solids and that kind of thing. So
I normally think of like resistivity or conductivity as like, how metal have like a sea of electrons, right? Kind of facilitate current flowing.
Yeah.
But when I think of crystalline structure that's are made of insulators, for example, like in rocks, there are a lot of non-metals and stuff in there, so I didn't expect it to have high resistivity.
Yeah, I think it comes back to the point that you said before where like, a rock is like you picture a rock and it's like 100%, like quartz or something, but actually they're really heterogeneous, and so then they do have some like materials inside of them that do conduct electricity, and so that's how you end up not having a like 10 to the 6 or something ohm meters.
So in terms of your work, do you do like analytical, or do you do analysis, or you do field work?
It's a bit of both. So usually we do field work in the summer, and then we spend the rest of the year just looking at the data that we collected, because it is quite complicated. Because it comes out as like this big, well, it's like a time series, and then we have to like do a bunch of filtering to it because there's a lot of noise from humans, basically. Like we're emitting electromagnetic noise all the time. So just trying to accommodate for that. And then for your transforming it and getting it into the frequency domain where we can actually kind of figure out how the resistivity changes with depth. Because if you have like a high frequency signal, it's only looking at the near surface because it attenuates really fast. But then the low frequency ones you can see quite deep. And so that's kind of how we figure out our resistivity structures.
Yeah, the electrical noise interesting because you have 1/f noise, 1 over frequency noise that is really strong in low frequency. But that's I think the reason I want to ask too about like the frequency because low frequency. What do you mean low, right? Like some people, I would say low is like 1 to 100 hertz, for example.
Yeah.
But maybe low is different for you.
Low is very low for us. So we sample between like about 1,000 hertz. I mean, if you have some fancy equipment, you can get higher frequency, but we usually sample around 1,000 hertz to 10,000 seconds. So that's 10 to the negative 5 hertz. And that's basically like dictated. So basically we install these equipment, we leave it for up to a week, if we want to see really deep. And then the lowest frequency we can get, you can't just like leave it forever and hope that you get like, the lowest existing frequency. It's dictated by basically the harmonics of the Earth's, like the ionosphere. So like basically you get a standing wave the size of the Earth, and that's the biggest, the lowest frequency you can get, essentially.
So your frequency has to be really low to pick up those type of
Yeah.
signals.
Well, and then for those, like I don't usually work on those surveys, like the really deep ones, but they can see down to usually like 300 kilometers. So they're looking at like a lot of the lithosphere-asthenosphere boundary is defined by magnetotellurics because it does have like a stark contrast in resistivity between like, the lithosphere and the asthenosphere.
So I think for those who think this 300 is a lot, I would like to point out that the radius of the Earth is like 6.3 thousand kilometers. So 300 kilometers is like we barely scrape the surface of the Earth. To me, it's weird how we can map things really well. Or like we have a map of like the magma, like, I don't know, the Earth core and stuff like. Oh, but like the instrumentation, we can only go down. It's not that much, isn't it?
Well, so all of everything below that, they're only imaging using like seismic tomography, which is actually a super precise way of measuring like phase changes. Because basically, like if you have an earthquake and you're making like there's like pressure waves or shear waves that creates, and shear waves can't travel through liquids, and so all of those boundaries are pretty well defined through that because if you see a pressure wave and not a shear wave, you know that it went through something liquid at some point, if that makes sense.
Oh, so we have a bunch of probes around Earth, like from different country and stuff. So when earthquake happen, we can measure the amplitude of each type of wave, and we can map out what's underneath you very deeply.
Yeah, and we actually have like honestly an insane amount of seismometers just like around. Like in Alberta, I have a friend who works for the Alberta Energy Regulator, and I think we have like hundreds of seismometers just like in Alberta, keeping track of every little earthquake that happens.
Did they just use them for tracking earthquakes, or do they have other purposes?
They have a few purposes. So a lot of it's so like when we had that earthquake in Fox Creek for fracking, like when was that? Like 7 years ago, maybe 10 years ago. They really upgraded their system, and it's keeping track of a lot of earthquakes and induced seismicity as well. So basically earthquakes that are below a magnitude 4. So if it hits 4, it's probably going to make the news, but anything below that, they're still keeping track of.
So I'm just curious, are you able to use magnetotellurics at all to track earthquakes?
Not really, but we can use it to do some earthquake hazard assessment. So we did a survey this summer on Vancouver Island, and one of the things that we're really looking for is like saltwater intrusion. So basically, you have the subduction zone, and then there's Vancouver Island, and you're building up a lot of stress there from the plate kind of moving underneath the other one. And then one day we're going to have an earthquake. And being able to see how much kind of buckling there is and how much fluid is in the actual fault itself, that can help with predicting how big the earthquake is going to be. Because if you have fluids inside of a fault, it basically lubricates it, and then you can have more movement than you would have had otherwise. And so that's something that we're looking for. And seawater is pretty conductive, so there we go.
I wonder if these technology have been used to, well, you said a little bit of geothermal, but so it also can be used, I guess, to find water underground, because I know historically people try to do that a lot, like, and there's some crazy wild stuff people do, like, oh, there's like two rod of metals and try to point to where the water is. It's like, well, I don't know if you heard about that method that actually like doesn't work at all.
Well, so for like fresh groundwater, usually they actually use like DC resistivity. So basically, you put a bunch of electrodes in the ground, and then you inject a current. Because our method, like we see from like 500 meters down, so you probably don't want to drill your well 500 meters deep. So it's actually not going to be overly useful. But yeah, so DC resistivity surveys are pretty cheap, I would say, and that would be a pretty good way to find fresh water. And that's the method they use for, like, there's Geophysicists Without Borders through like the Society of Exploration Geophysics, and they go to like Africa and Bangladesh, I think, to do these types of surveys, and they like train people how to use the equipment so that they can find their own water, and then they leave, essentially. Yeah.
Kind of cool.
Yeah, it allows agriculture where there's no like river around and stuff. Like my friend who has a farm, he actually spent quite a bit of money hiring like a company who basically find the underground water, and they guaranteed it. It's like they will keep digging. You pay like a certain amount of money, and they will keep digging until they find it. Like, well, they probably have a good way to actually test if there are water underground, or there is water underground or not. If not, they're gonna lose a lot of money by just digging 100 holes right on the property.
Also, wouldn't be very nice for your friend's property. Just these death pits everywhere.
There's like long cylindrical.
So in terms of geothermal, you know that looks different. It has a different conductivity. How do you actually use that information and apply it?
So there's a couple. So my research area that I'm working on right now, we're trying to basically image, like, so there's a fault running through the area so there's a hot spring at the surface. That's our first hint that there's going to be geothermal there. It's on the coast of BC. That used to be a subduction zone. So basically, you get these subduction arc volcanoes, but it's no longer. So basically, you have this heat come up, and it's still there, but it's no longer active. And then you have a hot spring, and we're wondering where the hot spring is coming from. There's a pretty well-known fault that runs through the area, but it's not very well constrained in our actual valley because of a lot of sediments at the near surface. You can't see it or map it using geology. And so we're trying to basically figure out where the heck that hot spring is coming from. The hot spring is going to be transporting hot water, which, like I said, conducts electricity pretty well. So what we're looking for is like and the valley is basically entirely made out of granite. So you have like a giant granite section with a fault with hot water running through it, and so it should show up pretty well where the fault is. And so now they're trying to, based on our resistivity model, which has this little conductor that's running through it, They're trying to drill to see if the water inside of that conductor is actually hot or if the conductor is something else. Because, unless you're drilling something, there's no way to tell if it's, maybe clay or something, maybe not actually hot water from the surface. It all looks the same in your resistivity map. But in not my research area, in other like hotter areas like volcanoes, or the Great Basin in the US, if you get to really, really hot temperatures where you're doing like clay alteration temperatures, what you're actually looking for is not a conductor. You're looking for underneath the conductor. So basically what happens is like you have these volcanoes that come in, they make everything super hot, and then when it's hot, it creates these clay layers that conduct electricity really well. And those are like, and they also work as like a cap rock, like similar to a hydrocarbon. So where fluids would be coming to the surface before, now they're trapped underneath this conductive clay layer. And so if you can see this, like they call it a clay cap, if you can image this clay cap using our method, then you can drill basically through it and find super hot water. But that's like, so basically you're like looking for a conductor, but like for a different reason. So it's like, it could be hot water, it could be a magma chamber, it could be a clay layer. And so that's where it's really important to talk to geologists as well to understand kind of your setting and what could possibly, all these like conductors could be. Because it could be a lot of stuff.
Oh, actually, like I'm curious. Well, I think it's more for more general audience on geothermal, because I feel like the general understanding of the ground is like it's kind of cold, right? Like can geothermal happen anywhere? Because I guess if you dig deep enough, it would get really hot, right? So, but like, is that true? Generally, like because like let's say I want geothermal heating. Can it be done anywhere? Is there a specific place that you can do it?
So the heating can happen anywhere. So have you ever been in a mine? Maybe not. Okay, so I toured a potash mine in Saskatchewan, and I think it was like 2 kilometers down. The elevator ride was quite long, is all I gotta say about that. And it was unbelievably hot down there. Like 36 degrees, and they had like a fan circulating the whole time trying to cool it off. So it does actually get quite hot quite fast. There's only a few places where you can produce electricity from geothermal. But as far as heating goes, the ground is quite hot, which is why we have basements, right? Is because the pipes don't freeze in the ground. So like even if the ground is frozen up at the surface, the second you get into the ground, here in the basement, it's probably like 5 degrees, which I know you're thinking, that's not going to heat my house. But even if you go like a little bit further down, you get a couple extra degrees. And you can actually heat your house using 5 degrees. So the idea is that, if we had like radiators, like you're using water, usually what you would do is you'd take cold water, you would heat it, and then you would heat your house using it. If it's minus 40 outside and you're heating your house to 5 degrees, you only have to heat your house an additional, and then they also use it for cooling in the summer. So that's that whole geo-exchange system.
Yeah, I find like I think in normal people experience like when you go to the basement, it's usually cooler instead of hotter.
Oh, I just know there's a newer technology. So we've talked about heat pumps before, where they're able to essentially pump heat with a coefficient of performance greater than 100%. And I think they can go up to like 500%, or 5 times the energy you put into it is extracted from it, because it transfers energy between 2 different sinks. But they also have in-ground heat pumps that you can get for your house. So they put them like 20, 30 feet underground. And that way they work well at minus 40 or at plus 40. because the ground will stay a pretty consistent temperature.
Yeah, we actually have a project in Nunavut this year, so I'm going up to Resolute Bay, which is like as close to the Arctic as the North Pole as you can get. I think it's the second northernmost community. But anyway, they're looking to get some geothermal energy going up there, not to produce electricity, but to heat their houses. Because, yeah, I mean, they basically ship in diesel to heat their homes at the moment. And so if you can get it from, minus 40, minus 50 to 5 to 10 degrees, and then you use diesel to get you that extra bit of comfort, that's basically the plan.
I feel like if you can dig deep enough to get really hot, you get basically infinite, unlimited amount of heating for basically one investment.
But then the issue is that like, so every kilometer you dig is it's like $1 million, I think, per kilometer is like a drill pipe. The other thing is like, then you have an extra kilometer of pipe to maintain, and you have to pump all that water. So one of the biggest costs in like energy costs, like not actual costs, is like the actual pumping. So if you have a geothermal power plant, so there's a deep project in Saskatchewan that they're building, and I'm pretty sure 30 to 50% of their electricity that they're going to be making is going to be powering their pumps. So that's a big issue.
All right, so you still need to power the pump, so in a way you have to use some kind of auto fuel anyways.
Yeah. So like they're using their own electricity to use it, but then it's like, the deeper you go, the less return you have, and then so you're trying to meet in the middle somewhere there.
Yeah, I don't know how geothermal really work. I thought for a long time it was like, I could put like a solid copper rod in the ground and just get it to conduct heat up. So I have to, there's no hollow, there's no nothing, just like bunch of rods.
Yeah. So basically, like a conventional geothermal plant is essentially two pipes. There's like the injecting well and the extracting well. And what you want is some porous, permeable rock, so like a nice sandstone or something at the bottom. And then, but you don't want it to be too permeable. And then you drill these two holes like 3 kilometers apart. And so you're injecting a ton of water in one, and you're sucking up hot water on the other side. And what the water is trying to do is absorb a bunch of heat as it propagates through the reservoir. So that's the issue. Like if you have too much permeability, it'll go too fast and you won't actually absorb heat from the rock. But if you go too slow, then you're using too much power from those those pumps that we were talking about. And then so it's a pretty big optimization problem, which is kind of exciting but pretty tricky.
Oh. The process is different than what I thought completely. I thought it's just conduction, but it's actually use water to carry the heat. I guess that's more.
And then you're basically fueling a turbine. Although you do most of them use like organic Rankine cycles. So you'd use a heat exchanger to move the heat from water to like a different fluid, like a glycol or something, and then you power the turbine using that. But that's getting maybe a bit specific.
So I guess just moving on to other work that you've done. You mentioned going up to Resolute Bay. And I believe a few episodes ago in our intro topic, we talked about some interesting results about the existence of subglacial lakes. And I know you were involved with that project a little bit. So can you tell us about that a little bit?
Yeah, so they're publishing a paper right now, hopefully soon. It's in review. For a project on Devon Island, which was just off of, just across from Resolute Bay, essentially. And so they found, quote unquote, a subglacial lake underneath the ice cap there. And in order for it to be there, it had to be, hypersaline, which, anyway, so basically they found it using only radar data. So you fly, a helicopter over this area and you shoot a bunch of radar. And so they wanted to go back and do actual ground surveys because ground surveys are a lot higher resolution because you're closer to the ground and you can use like kind of fancier equipment than the helicopter ones. So they used 2 different types of electromagnetic like methods because you can see if it was a super salty lake, it would show up as a very strong conductor. So they used magentotellurics, which is my method, and then, which is why I went up, because I actually trained the field crew, and then time domain electromagnetics. So that's basically you install a really, really big wire, I think they used a 500-meter loop. So they set out a 500-meter loop of wire, if you can imagine it. That's like the size of, I don't know, bigger than a baseball field, I think. If you can imagine it, like probably twice the size of a baseball field. Anyway, it's literally huge, but you're out on an ice cap, so there's nothing in your way. And then they put a current through that wire. You make a big magnetic field, and then you shut it off. And that magnetic field is inducing eddy currents, which then propagate into the ground. You have a receiver coil in the middle, which is measuring the secondary magnetic field. Are we following? Okay, good. A secondary magnetic field, and that's going to tell you about like the resistivity structure. And that one is, the reason they use that one with my method is that you see higher resolution and shallower. So then you can combine them both to kind of fill in the gap. And then they also used refraction seismic. So basically they're making little earthquakes at the surface. They bounce down, hit this water layer and bounce back up. And if you're hitting water, you're going from a solid material to a liquid. So it should have like kind of a distinct signature. So they went out and did that, and there's no lake there. So now they're like looking over all the other kind of catalogs for subglacial lakes throughout the world because they've identified, I can't remember, 120 just based on radar data. And so now they're like looking to see, because now they've like reprocessed the radar data and the refraction index. Anyway, what they use to kind of process the data, they used a coefficient that was like too large. And so now they're thinking, okay, well, is this like an industry standard where we've kind of all gone a bit astray?
That's pretty cool, actually.
It's a bit awkward.
It's really cool that kind of the method you guys used or came up with, you kind of like turned the tables in science in that field. It's like, oh, how many of these are actually these lakes?
Well, and I mean that's just the trick. Is like I think they're gonna have to change those to like hypothetical lakes, because I think what you're gonna need to do is actually go physically and collect more data, and then I think they've kind of developed a method, of double checking, before, because they were planning to drill it, I think, which would have been really, really expensive, and a waste of money now that we know that it's not there. So
yeah, maybe they might. I imagine they'll use kind of the method you guys are using, and they'll maybe correct their radar data method. They'll find an actual lake somewhere underground. They'll apply your method, determine that it actually exists, and then they'll do some other detection methods and make sure that they work, and then they can use that in the future, maybe. I don't know if that makes sense or not.
That does make sense.
So I want to move on a little bit and want to hear your story. How do you get into physics or geophysics or even earth science in general?
It's maybe a bit embarrassing. My dad's a geophysicist.
Nothing wrong with that.
Yeah, my dad has his PhD also in geophysics, so there we go.
So were you exposed to these since you were young? That's why you got interested in it?
So I grew up in Calgary, and I used to spend a lot of time. I still do spend a lot of time with my dad, and we always go like hiking, and he would like show me all the rocks. And then, when I graduated high school, I was like, I think I want to go into math. And then, I actually started out in math, and then I was like, I don't know about this. And then, I switched into geophysics because studying math is really cool, but it gets like having a direction to move your math studies is definitely easier, I
Yes.
find.
100%. At least, yeah, I'm the same way.
It's like I can use statistics if I have a data set that I understand, but if I'm like using statistics for statistics' sake, it does not. My brain cannot.
Well, it sounds like the next guest gonna have a teacher. We need to have stats person next.
My brother's a statistician, so there we go. I think his master's is in Bayesian statistics, and he like uses satellite data to track like building rotation / tilting. So like when they make those like super tall skyscrapers, they're all moving slightly. And he works for a consulting company in Vancouver that like keeps track of the acceleration of skyscrapers.
Well,
Oh wow!
that's
It's
pretty
pretty
niche. I've
crazy.
never even heard of that.
Right? Me
Yeah,
neither.
I didn't know they need to keep track of that. That probably for
It's probably a
construction
good
engineering
idea.
sake.
Yeah, I thought they just
Yeah.
kind of before they built
They just kind of look
before they
at
build
it.
the building, they kind of like factor all that stuff in. Then they build it, and they're like, "All right, it's good," and they just leave it. I didn't realize they monitor it.
Mhm.
I guess with really tall buildings, like the CN Tower and stuff, you'd need to do that, I think.
Yeah.
But
Well, and especially when they're built on like sand and stuff, it's yeah. You never know what the rocks are gonna do. Your building could be perfectly fine, but what are you building it on?
yeah, good point.
So in terms of the past. So let's talk a bit about the future. What are your hopes and dreams? What do you like to achieve, or what do you like to do exactly? Why who do you see yourself being in the future?
Yeah. I would really love for geothermal to take off, and then I could get a nice geothermal job and change everybody's lives and whatever. We'll see if that actually happens. It looks like it might. I would also really like to work for the government and make like big, like those like big maps of like geothermal potential. I feel like that would be really cool.
Professors?
Academia is cool. I'm not sure if I want to go. I don't know.
I feel like people who become professors, I mean, I want to be a professor, but it's because the stuff I study isn't, it's not like, I mean, maybe I could go into industry, but the more theoretical you get, the more kind of towards a prof you tend to, I think.
And I don't know a single prof with like a nice like work-life balance.
Yeah.
So it's like a bit like, it would be cool, but
Yeah.
do I want to be answering my students' emails at like 11 p.m. on a Sunday?
Yeah, that's kind of the route I'm going, where the more I'm getting into it, I always want to be a prof, but I'm like, you're right. Every prof I've ever met, they have no work-life balance at
It's
all.
like a
Yeah,
workaholic.
and I am too, but I don't know if I want to be for the rest of my life.
Well, yeah, that's the thing. It's like, okay, yeah, I'm a workaholic, but like, hopefully one day I'll be working 9 to 5, and then it'll be 5 p.m. I'll be like, okay, looks like I'm going home, and then not doing anything when I get home. Not like, oh, I'll check my email. But
Just from experience, I find a lot of people in like earth sciences want to not be a professor. And I think government job is the ideal place to be, where you get all the benefits of working in the government, but you still get to do science.
yeah, one of our PhD students who finished when I started, he now works for NRCan, and I'm like, oh, do you need an assistant, please?
What kind of government of Canada science jobs are there? Because I know there's a lot of like earth science ones, but I
lot.
remember looking into it years ago. I was like, I wonder if there's any like physics positions for the government of Canada, and I think most of them just like boil into like you do math to like optimize, or you do statistics, or you end up just going into like earth science in some way.
You can do like cybersecurity as a scientist
Yes,
too.
that's a newer one, isn't it? Well, relatively.
I I know the CSA very rarely has job postings, the Canadian Space Agency.
I thought NRCan hired physicists.
A lot of places will hire physicists
Pretty
just because they can do
sure.
math and problem solve. You can kind of teach them. Like if I suddenly decide to go do earth science, it'd be a big transition, but I can do math. So, or if I decide to go work for a bank and do business, I can do math. They can teach you the language over a few years, but the fact you can do math, they really love that for some reason. Like a lot of physicists go and work for banks, or they go and do statistics or stuff like that, or like data analysis.
Well, are there any final questions or comments for Zoe?
Oh, I have a comment. Okay, so when I was hanging out with Patrick, I don't know, a few weeks ago, he was like, oh, a lot of our scientific discoveries happened more than 100 years ago. And I was like, oh, we still don't know anything about the Earth, actually. So, like, my master's thesis, I always thought that, like, plate tectonics was pretty well established. But then turns out it's only, like, 50 or 60 years old. And then the other thing is that the mid-ocean ridges are spreading, like, 4 times as fast as they should be, and we don't know why. So it's a mystery. The Earth is a crazy place.
Earth is much.
I mean, we don't know why the universe is expanding
on that
at
note-
the accelerated rate.
We know a lot more about like space than we do about the Earth. I think, though.
We do,
Like,
yeah.
There's a lot less stuff out in space. Well, that's the wrong way to word it. I guess there's a lot of like gas and emptiness in space and stars, but like the Earth it's really complicated when you zoom in on the Earth and the oceans and stuff. I guess like we've explored more of space than we
Yeah.
have our own ocean, kind of thing.
Let's go. The celestial structure. It's kind of more obvious, right? Because you look at the sky and just get data from it. But on underground, you have to find a way to penetrate all these barriers to get to the data you want. And like you said, like what's it called? The way we do it now through seismic stuff, that's like indirect, right? Like that's kind of tough. The hard we can only drill maybe kilometers or a few more, right? Like compared to 6,000 kilometers that we have in terms of radius, that's nowhere near. And I think we will be able to drill that far anyways. Like everything would melt. What's the point, right? So we have to find an indirect method of measuring all the stuff that we need to do. And maybe who knows? Maybe this Earth's gonna blow up in 5 years, but we have no idea because we never really drilled into it and see like, oh yeah, there's a movie that they go to the core of the Earth to drop nuke. I don't know which what's it called anymore. Yeah, there was like you have to do to the core of the Earth to drop nukes to it so it doesn't stop or something like that. I remember watching that when I was young. I thought it was somewhat realistic, but
Imagine that something's going wrong and your solution is to just nuke it. Like let's
it's an
let's
American
nuke
movie.
Mars and terraform
For
it.
some reason in like first year geology classes or like extracurricular geology stuff, we always watch like the worst geoscience atrocities, and then we're like, what's wrong with this picture? And it's like, what is that movie, like 2020?
2012?
Yeah,
2012? And like the plate they're like, the plate tectonic, like the plate is flipping. It's like, what? That's like not
Yeah.
possible.
Plates flipping.
Yeah, it's that what's called axial shift, right? Like
Yeah, they're like the San Andreas fault just like buckled off and California flipped over.
the
It's like,
movie I
what?
was talking about is called The Core. It says the Earth's gonna
Oh,
stop
yeah.
spinning, so we have to nuke it to get it to spin again.
Incredible.
Imagination.
Well, it seems like there's a lot of mysteries left in physics and in geology and in geophysics. So if you want to go explore and become a geophysicist, whether your dad is one or not, there are some ways in which you can contact our guest and you can contact us and we can contact our guest. The first way is emailing us. We are at the Hyperthesis Podcast at gmail.com. So that's hyperthesispodcast@gmail.com. You can send us an email if you have any questions, if you have any suggestions for episodes, or if you want to be on our show, you can send us an email, let us know what your area of expertise is, and we'd be more than happy to have you. If you want to reach out to just Zoe, do you have a way people can reach you?
You can email me at Vestrum, so ZVESTRUM at ualberta.ca.
Yeah. So if you have any questions about this episode, specifically for Zoe, you can send her an email. I'm sure she'd be more than happy to answer your questions. She has to answer, actually not so much anymore, but lots of undergrad questions. So feel free to be in that lineup. And if you want to contact any of us, you can also find us on Instagram. We're at the Hyperthesis. We post updates about when we are posting episodes, as well as some behind the scenes looks and some memes. Liam has gotten better with posting memes, so good on you, sir. You can also find us pretty much wherever you find podcasts. So we're on Apple Podcasts, Google Podcasts, Amazon Music. We're based out of Spotify. Anchor FM no longer exists. It merged with Spotify, so we're based out of a Spotify service. But you can find us pretty much wherever you find podcasts. And we are also on YouTube. So there are many ways to find us, and you know how to contact Zoe. So feel free to reach out if you would like. And now we're going to do a very quick story, extremely quick. And this was actually brought up a bit earlier by Zoe about how plate tectonics exactly work and how they were discovered. So the idea that land masses are moving underneath us constantly is fairly new, and only really originated in the middle of the 20th century. So the idea of plate tectonics, which we know now is the movement of these large land masses on a less dense fluid that's circulating. We talked about the different layers of the Earth, so it's part of the mantle. That's circulating and moving these land masses. This was really unknown even about 100 years ago, maybe a bit more than 100 years ago. Also, Zoe, feel free to correct me if I get anything wrong. However, the first suggestion of the movement of the crust of the Earth was from Alfred Wegener in 1912, based on the idea that continental bodies that make up the crust of the Earth are somehow able to shift slightly in different directions. Now, he later expanded on this theory 3 years later in 1915 with his book titled The Origins of Continents and Oceans. In that book, he proposed that the continents were at one point merged together into a single land mass, which we today now call Pangaea, and that these land masses drifted apart like very slow-moving icebergs floating on a sea of denser liquid material. He had names for the less dense crust of the Earth that was floating, which was called Seal, and the more dense sea of liquid was Sima. Now, there was some supporting evidence for this that was first evident on maps. Now, we didn't have any satellite imagery at the time. Artificial satellites didn't exist, but we had really accurate hand-drawn maps. And by looking at the west coast of Africa and the eastern side of South America, you can see that they kind of fit together. And there are other instances for maps in which we can see where things might actually fit together quite nicely. Now, there was also evidence of different species existing across oceans. So, for example, there were certain types of fossil plants that existed both in South America, or that were found in South America, and also in Africa. And so the fact that these are plants, they don't really like to migrate too much. They were found in very different places, again, separated by an ocean, but they're pretty much identical. And there are also several types of mammals and reptiles and other flora and fauna that were found oceans apart, but they were pretty much identical and in similar places in the fossil record. So this evidence was pretty telling about the possibility of continents moving. And it was around 1937 that a South African named Alex du Toit apologies if I mispronounce that, put together a mass of all this information in a publication known as Our Wandering Continents. And he recognized the ideas of Wegener and then built upon them using this evidence. Now, these ideas were not widely accepted at first because there wasn't really reason to support the actual movement of plates. We didn't really know the physical mechanisms or the convection currents that take place within the mantle. And so it was just assumed that the Earth was quite solid for the most part. There might be a liquid core, there might not be. But our technology and our knowledge weren't very extensive about the center of the Earth or what's underneath the Earth at that time. It sounds like it's still pretty limited, but we're better than we were 100 years ago. Now, there was a lot of opposition to these ideas because of it. However, as we got more evidence throughout the 20s, 30s, and 40s, there were different discoveries such as the existence of a liquid mantle or parts of a liquid mantle, along with the evidence of convection currents within that mantle that may have caused the movement of plates. We also have other evidence, such as the Mid-Atlantic Ridge or other oceanic ridges that exist and kind of are splitting apart. And we can actually measure that split now. And as Zoe said, it's going faster than what we expect. So again, still a lot to learn. But with the evolution of better experiments and better data taking, we were able to essentially discover a lot more evidence that very heavily supported the idea of plate tectonics. So everything from the sea floor spreading and subduction happening to looking at paleomagnetism and how that has changed over time, which can come from a couple things, but continental drift is one of those. And the paleomagnetism is just looking at essentially the orientation of magnetic fields in a rock record and seeing how that orientation has changed over time. Now, it was shown in the late 1950s that there were essentially two occasions that the data proved the validity of continental drift, both by Keith Runcorn and Warren Carey. And these evidence kind of cemented it in place. And as was brought up just a bit earlier, we noted that there weren't really a lot of paradigm shifts in the last 50 years. This one is just on the cusp, but this was a major paradigm shift where now we saw, okay, there's strong evidence for tectonic plates to be moving on a liquid mantle, causing the plates to shift and the land masses of Earth to shift. That's now widely accepted today. It's not really controversial in the scientific community. Probably other communities, they have some things to say about it, but generally it's something that's regarded as true and something that happens, something we can measure constantly. And there's still a lot of interesting research to go into exactly different mysteries that are involved with continental drift and how it's affecting us, everything from earthquakes to volcanoes, and if we'll have something like Krakatoa 2.0 in Yellowstone National Park. So there's still a lot to learn about plate tectonics and continental drift, but it's very interesting how recent this theory is and how much science developed within the span of about 40 years to go from, okay, this might happen to, okay, we're positive that it does happen.
All right, perfect. All right, thank you very much, Zoe, and thank you, Patrick, for
thanks.
the story. All right, then I'll talk to you guys next week, hopefully, or next episode. Take care.
See ya.
Bye, everyone.
Bye.